Okay, so hi everybody, welcome back. So we finally have reached the end of the semester, and this is going to be our very last video. Now, in this video, I'm not going to throw any new material at you. I think it's too late in the game for that. Instead, what I'd like to do is a recap of the entire course. So we're going to start at the very beginning and just go through all of the topics, all of the most important concepts and equations that were covered throughout the semester, and just make sure to highlight each one. But since there's so much to cover there, I can't really go into any detail into any one of these things, and we're not going to be going through any example problems. So instead, think of this sort of like a list of topics and equations, and you can use any one of these topics that we hit on as a jumping off point for your studying. So for example, if we touch on a certain topic, you can be pretty sure that there is an example problem in the review packet or in the end of lecture problems that you can go through as a way of practicing on that particular topic. But again, what we're going to do in this video is sort of more like a summary without going into any particular detail on any one topic. Okay, so let's get into it. So we're going to start with chapter 19, which covers the first law of thermodynamics. Now, in this chapter, there's an emphasis on ideal gases. So let's go over the ideal gas law first. So the ideal gas law says that the pressure times the volume of an ideal gas is equal to the number of molecules. So that's what capital N represents, number of molecules, times Kb, which is called Boltzmann's constant, times T, which is the absolute temperature. In other words, we have to use the Kelvin scale when measuring temperature if we're going to use the ideal gas law. But there's another formulation of this, which is P times V is equal to lowercase n, where this is now the number of moles of gas, times R, which is a different constant called the ideal gas constant, times T. So there are these two different ways of formulating the ideal gas law, so just remember that. And using the ideal gas law, we derived a really important result. So for an ideal gas, what we found is K bar is equal to 3/2 times Kb times T. And what this is saying conceptually is that the average kinetic energy of the gas molecules, okay, that's what K bar is on the left side of the equation, that's directly proportional to the temperature. In other words, this gives us an interpretation of what temperature is on a microscopic level. If you have an object that is very hot, that just means the molecules have more kinetic energy. They're moving faster. And if it's colder, the molecules are moving more slowly. They have lower kinetic energy on average. So that's really what temperature is at a microscopic level. But we'll also remember that kinetic energy is just 1/2 times the mass of a molecule times v squared. But if we're talking about an average, we'll put a little bar on top of the v squared. That's equal to 3/2 Kb times T. And so if we solve for the speed of the molecules, this will be what we call the RMS speed. That's going to be, well, cancel out the 2 and then divide out the m. So we have 3 Kb times T over m, and then take the square root. This tells us what a typical speed of one of these molecules is, okay? So the next thing we learned about is how do we apply the first law, which, by the way, is just conservation of energy. Okay, the first law of thermodynamics is nothing more than a statement that energy is conserved. But how do we apply this for an ideal gas? Well, this is what it looks like. Q is equal to W plus delta E internal. So in this equation, the variable Q stands for the heat that's flowing into the gas or out of the gas, depending on the sign. So there's not really one formula that always applies here, but I'm going to show you a few examples just hopefully to refresh your memory. So if we have a constant volume process, then the heat for that process will be given by lowercase n, that's the number of moles, times CV, that's the constant volume molar specific heat, times delta T, the temperature change. So if delta T is positive, that means heat is flowing into the gas. That means Q is positive. If delta T is negative, that means Q is negative. On the other hand, if we have a constant pressure process, then Q is equal to N times Cp times delta T. So there's basically a different specific heat when it comes to a constant pressure process. And keep in mind, these are not the only two types of processes that can happen, but those are the two that we have sort of ready-made equations for. Okay, so the next is the work, that's W, but this is the work done by the gas in particular. Now this is given by an integral of P dV. And again, I'm not going to say anything more specific than that because the exact formula for the work that you'll get when you do this integral depends on the type of process that's going on. So actually, heat and work here are what we call process variables, meaning the actual value of heat and work depend on the type of process that's happening. Now, the last thing is delta E internal. That's the internal energy of the gas. And it's changing, so it's the internal energy change of the gas. Now, this is given by delta E internal equals NCV delta T. And it's important to note that this applies for any process. And so internal energy would be an example of a state variable. So if I want to know the internal energy of a gas, I don't need to know the process that took the gas to its current state. I just need to know what the current state of the gas actually is. In other words, I just need to know the temperature of the gas to know its internal energy. I don't need to know how it got to that temperature to know what its internal energy is. So, with that said, let's talk about ideal gas processes that we need to know about. And there are four. The first one is called the isobaric process. And this just means that we have constant pressure, or delta P is equal to 0 for the process. The second one is called isochoric, which means the volume is constant, or there's no change in volume. Delta V is equal to 0. We also have isothermal. This means the temperature is constant, so delta T is equal to 0. And then finally, we have an adiabatic process. Now, the defining feature of an adiabatic process is that Q is equal to 0, meaning there's no heat flowing into or out of the gas during the process. Okay? Now, for each one of these processes, we should know what it looks like when we plot them out on a PV diagram. So remember, a PV diagram shows the pressure of the gas on the vertical axis and the volume on the horizontal. Okay, so let's plot each one of these processes out on the PV diagram. So let's put a point on the diagram. Let's say that's our initial state. And so any process is just a line on this diagram which takes us to a final state. So if our process is isobaric, that means the pressure stays constant throughout. And so what we have is a line that's just completely horizontal at one fixed pressure. So this would be an example of number 1, an isobaric process. On the other hand, if we had a vertical line like this, that would indicate a constant volume, or an isochoric process, that's number 2. Okay, for an isothermal process, the temperature is constant, but pressure and volume are not necessarily constant. Let's actually just go back to the ideal gas law, PV equals nRT. So that means P equals nRT divided by V. Now, if temperature is constant, that means pressure is just inversely proportional to volume. In other words, the curve should be something like this, where the pressure is inversely proportional to volume. So that would be an isothermal process, number 3. Now, an adiabatic process would look kind of similar. It's a curve that slopes downwards like this, but it's even more steep than the isothermal curve. So this is number 4, adiabatic. Now, it's important to remember that specifically for an adiabatic process, there is a relationship between pressure and volume, which is that P times V to the gamma power is constant. So that's what the curve I'm showing you on the PV diagram is. Basically, P times V to the gamma power is a constant. And there are other relationships to know between pressure, volume, and temperature, but this is just one of them. Okay, so just make a note that there are other adiabatic relationships between pressure, volume, and temperature that you should know about. Now, what is this gamma thing anyways? Well, that takes us to degrees of freedom. So remember, the degrees of freedom given by lowercase f represents the number of independent ways, I should say, that the gas molecules can have energy. So the degrees of freedom is the number of independent ways that the gas molecules can have energy. And what you should know, as far as degrees of freedom are concerned, you should know monatomic gases and diatomic. Okay, so you should know those two cases and how to handle the degrees of freedom. But once we have a handle on what the value of F is, well, that goes into our formula for CV. Okay, the constant volume molar specific heat is just F over 2 times R, where again, F is the number of degrees of freedom of your gas molecules, whereas Cp is F over 2 plus 1 times R, and gamma, well, the definition of gamma is actually just the ratio of Cp divided by Cv. It's the ratio of those specific heats. But if you plug those in, you can find that gamma just depends on F. It's just 1 plus 2 over F. Okay, so that's what the gamma up here is referring to. So let's move on to the next chapter, which is chapter 20. And the topic is the second law of thermodynamics. So if you remember, the first thing we talk about in chapter 20 is heat engines. And basically, what is a heat engine? It's any device that takes heat as an input and outputs work. Okay? And the basic schematic of any heat engine looks something like this. you have a high temperature region where the temperature is TH. You have a gas, which is what's performing the work in your heat engine, typically by pushing a piston in and out. And then you have a low temperature region, TL, down here. Now, throughout one cycle of the heat engine's operation, it's going to take in some heat from the high temperature region, which is QH. Of course, we want the gas to do some work, so there's going to be some output of work, W. But there's always going to be some exhaust heat, which we call QL, which goes from the gas to the low temperature region. And that actually can't be avoided. Okay, you can't just take in heat and convert it all into work. There's always going to be some exhaust heat. So if we take the first law of thermodynamics and apply it to the heat engine, specifically for one cycle, one complete cycle of operation, then this is what we get. Absolute value QH is equal to the absolute value of QL plus the absolute value of W. Again, the idea behind this equation is the gas takes in some heat from the high temperature region, and then what does it do with that heat? It performs some amount of work W, but it also exhausts some of that heat into the low temperature region, which is QL. Okay? And this is just how we state that energy is conserved throughout the cycle. Now, one thing we're always interested in when it comes to a heat engine is efficiency. Now, efficiency is what you get out divided by what you put in. Okay, so epsilon stands in for efficiency. That's equal to, what do we get out? Well, that's work. So the absolute value of W goes on top. And then what do we put in? QH, right? That's the heat that we have to pump into the engine in order for it to operate. Now, actually, there's another way of writing this equation out, because if you take the equation up here, you can see that W is QH minus QL. So we'll have QH divided by QH, which is 1. And then we'll have minus QL over QH. So these are just two equivalent ways to think about the efficiency of a heat engine. But here's the thing. Even under perfect conditions, so among these perfect conditions, we assume things like no friction. But even under perfect conditions, 100% efficiency is impossible. So the maximum possible efficiency of any engine is not 100%. Instead, it's given by the Carnot efficiency. Okay, and the efficiency of a Carnot engine is equal to 1 minus TL divided by TH. So you can see that this is never going to be exactly equal to 1. It's always going to be something less than that, which means, again, 100% efficiency is not possible. So a few things to note. You should know the Carnot cycle. In other words, you should know all the different processes that go into the Carnot cycle and how they fit together. Also, you should know about refrigerators and heat pumps. So you can take this same sort of analysis that we've applied to a heat engine and talk about refrigerators and heat pumps. Okay, so I'm not going to go into that here, but just take note that that's something you need to know about. Okay, And that finally takes us to entropy. Now, entropy basically is a way of quantifying the amount of disorder in a system. And there's a definition of entropy, the Clausius definition, which goes something like this. Delta S, the change in entropy of a particular system, is equal to the integral of dq, that's some infinitesimal amount of heat that we add to the system, divided by T, that's the absolute temperature of that system as this is happening. So in general, we have to perform an integral to calculate an entropy change. Now, as a side note, this is the Clausius definition. You should also know the stat-mech definition of entropy. But we're not going to go through that here. That's just something you need to know about. So the second law of thermodynamics has to do with entropy. And basically, here's what it says. In any real process, the total entropy of the universe will increase. So how do we sort of write this out as an equation? Well, the entropy change of the universe is what we're referring to in the second law of thermodynamics, delta S universe. And that's always going to be equal to delta S for your system, however you choose to define your system, plus delta S for the environment. And of course, if we take the system plus the environment, that's the universe. So delta S for the universe is always positive. In other words, the entropy of the universe is always increasing. And that leads to all kinds of interesting consequences, like irreversibility of certain processes, and the idea that the universe as a whole will eventually reach what we call heat death. But this is the idea behind the second law. So that takes us to chapter 15, which deals with mechanical waves. So let's start with the definition. What do we mean by mechanical waves? Well, mechanical waves are patterns of oscillations which propagate through a material. Propagate just means moves through. A material at a certain speed. Now there are two basic types of mechanical waves. We have transverse. In a transverse wave, the oscillations in the material are perpendicular to the propagation of the wave. So in other words, the material is oscillating in a direction that's perpendicular to the direction that the wave is moving in. Whereas in a longitudinal wave, the oscillations are parallel. They're in the same direction as the direction the wave is propagating in. Okay, so that's the difference. So one thing that I showed you in this chapter is that any type of wave, regardless of its shape, can be built up from a combination of sine waves. So the sine wave, in other words, is like the fundamental building block of all types of waves, which is why we spend so much time focusing on it. So let's take a look at a one-dimensional sine wave with no energy dissipation. Okay, so there's no energy loss as the wave moves through the material. So the general form is d of x and t equals a sine kx minus or plus omega t plus phi. Okay, that is the general form of a one-dimensional sine wave. Now, if we plot this out, d stands for the displacement of the wave. And it's not only a function of position x, but it's also a function of time t. So if we take a snapshot of the wave at a particular moment in time, let's say t equals 0 as an example, then we're plotting the displacement at that particular time on the vertical axis, and on the horizontal axis we have the position x. Okay? So the wave will look something like this. It'll look like a sine curve. And there are a few things that we can immediately pick out and label. The first is the amplitude. So this is the amplitude or the maximum displacement of the wave. We also have the wavelength, which is the distance between peaks. That's given by the variable lambda. Okay, but in our equation, we have this thing k. That's called the wave number. So k is just 2 pi divided by lambda. We also have omega. That's called our angular frequency. Now, omega is just 2 pi times f, which is the frequency of the wave. Or we can think of it as 2 pi divided by t. So here, the frequency, f, is the number of cycles per second, or just per unit time in general, that our wave undergoes as it oscillates. But the period, t, is just the inverse of that. That's how long it takes to undergo one cycle. So amount of time per cycle. So again, these are the inverse of each other. F is 1 over t. And the angular frequency is just another way of talking about how fast the wave is oscillating up and down, but instead of cycles per unit time, we're talking about radians per unit time, or radians per second. Okay? So those are all the different quantities that go into this formula here. You should also note, just as a side note, know how to use the 1D wave equation to test a solution. In other words, if you are given some function d of x and t, you should know how to use the 1D wave equation to test out that solution. Okay, so we're not going to go through that here. That's just something to take note of. Okay, next. The speed of any wave is given by v equals lambda f. That's the fundamental relationship between the speed, the wavelength, and the frequency of a wave. But if we're specifically talking about a transverse wave on a string, then the speed is given by the square root of ft divided by mu, where ft is the tension in the string, and mu is the mass per unit length of the string. So that's what determines how fast waves will move down that string. Okay. Next, let's define intensity of a wave. So the intensity of a wave is something we'll keep referring to as we go on to the later chapters. And the basic definition is intensity is the energy per unit time per unit area that passes through a surface. Okay, so you have a wave passing through a surface. The amount of energy per unit time per unit area passing through that surface is the intensity of the wave. Now, intensity generally will follow an inverse square law, which says that I, which is the intensity, equals the power of the source. So the amount of energy per unit time is the power divided by 4 pi r squared, where r is the distance. So what this is telling us is that intensity is proportional to distance to the minus 2 power. That's why we call this the inverse square law. The intensity gets smaller with distance according to this formula. Okay, so next, let's talk about standing waves. What is a standing wave? Well, a standing wave is a pattern of oscillations in a material, but that pattern of oscillations doesn't move. That's why we call it a standing wave. And so a classic example of a standing wave is when we have a string that's fixed or held down at each end. So we have a fixed end of the string here on the left, and then a fixed end over here on the right. This is the exact situation you would have, for example, on a guitar. So there are only certain types of standing waves that can be supported, given that we have a fixed end on each side. So to give you an example, this is a possible standing wave where we have these 3 different loops. We call the points of maximum displacement. We call these the antinodes. And then we call these points over here of 0 displacement. Well, we call those nodes. Okay, and you have nodes and antinodes across the string. So for a string held down at both ends, like we see here, the possible wavelengths are given by lambda n equals 2L, where L is the length of the string, divided by n, where n is just some integer. It can be 1, 2, 3, and so on. And basically, we need the fixed end on the left and the fixed end on the right to be nodes. We need those to be points where there is no displacement. So we get this equation by starting from that basic premise, that the fixed ends are nodes, they're points where there is 0 displacement. So the next chapter that we covered is chapter 16, which is all about sound. Now, usually when we refer to sound, we're talking about a sound wave moving through air. But keep in mind that sound can also move through liquid and even solid materials. But a sound wave in air is a longitudinal wave. And the speed that's typical of a sound wave in air is 343 meters per second, but keep in mind that's at a particular temperature. That's at room temperature, 20 degrees Celsius. So the speed of sound can actually change slightly with temperature. Okay, so how do we describe a sound wave mathematically? Well, one way we can do it is in terms of the displacement of those air molecules. In which case, we use the same exact equation I outlined earlier. The displacement of air molecules as a function of x, as a function of their position, and t, the time, is equal to a times sine kx minus or plus omega t. And I'm just going to leave out the phase constant phi here. It's not really important. But we can also talk about a sound wave in terms of pressure variations. So as the air molecules oscillate back and forth, the pressure at a given point in the air is going to move up and down, above and below some sort of equilibrium level. So these pressure variations are what we call delta P. Those are also a function of x and t. And what we derived in class is that this can be expressed as minus delta Pm times cosine of kx minus or plus omega t. So notice the pressure and the displacement are out of phase with each other. One's given by a sine, the other is given by a cosine. But the maximum pressure variation, sometimes called the pressure amplitude, is given by delta Pm. This is equal to 2 pi times rho VAF. Okay, so rho is the density of the air. V is the speed of sound. A is the amplitude. And F is the frequency. Okay, that's how you calculate the maximum pressure. And along with that, we derived an equation for the intensity, which goes like this. I equals 2 pi squared V times rho times A squared times F squared. Okay, so that's how we mathematically describe a sound wave. Now, related to intensity is something called sound level. So the sound level is a logarithmic scale for measuring sound intensity. And it more closely lines up with the way we perceive sound intensity. We measure it in decibels, or dB for short. So the sound level is given by beta. This is 10 times log base 10 of I, that's the sound intensity, divided by I naught, where I naught is a reference intensity, 10 to the minus 12 watts per square meter. So basically, if you plug in the sound intensity I, along with this reference intensity I naught, you get the sound level beta measured in decibels. So the last thing to discuss here, as it applies to sound, is the Doppler shift. So the Doppler shift is an apparent change in the frequency of a wave. So of course this would apply to sound, due to the relative motion of the source and or the observer. So basically, if the source of the sound wave and the person or the thing receiving the sound wave are moving relative to each other, you get a shift in the frequency. So the most general way to sort of draw the picture is you have a source, I'll label that as S, and you have an observer, I'll label that as O. And this line connecting the two is what we call the line of sight. Now the source, of course, is emitting a sound wave, but the source can be moving with any particular velocity. But it's only the velocity along the line of sight that we care about as far as the Doppler shift is concerned. So V source, which appears in our equations, is just the component of the source's velocity along that line of sight. And the same goes for the observer. If the observer is moving with some velocity, we only care about the component of that velocity along the line of sight. That's the observer. So F prime, that would be the shifted frequency, equals F, the unshifted frequency, times V sound plus or minus V observer, divided by V sound minus or plus V source. And how do we interpret the signs here? Well, you use the top sign for motion towards, and you use the bottom sign for motion away. And that will cover basically every possible example of the Doppler shift when it comes to sound. So next, we jump ahead in the textbook all the way to chapter 32, which covers reflection and refraction of light. And so this is the first chapter where we discuss light. So let's talk about what light is in the first place. We can think of light as an electromagnetic wave. So to really get into the details of this, you need to have taken Physics 46 and really understand electricity and magnetism at a deep level. But for our purposes, we'll just say that an electromagnetic wave consists of oscillating electric and magnetic fields, so E and B fields. And those oscillating E and B fields travel through a vacuum, so they're capable of traveling through perfectly empty space, and the speed of light in a vacuum is what we call c. So when you have an electromagnetic wave, aka light, traveling through a vacuum, the speed is c 3 × 10⁸ meters per second. So the interesting thing about light is that it doesn't even need a material to move through. It's not a mechanical wave like what we've seen before. It's a wave that can move through perfectly empty space. But light can also travel through materials, such as glass. So in materials, light travels more slowly. And the way we quantify this is we say the speed of light in a material V is equal to the speed of light in a vacuum C divided by n, where n is what we call the index of refraction of the material. Okay, so the next thing we should think about is how do we visualize a light wave moving through space? What can we do to make a diagram or a basic picture of what's going on when we have a light wave moving through space? So the basic picture is this. If this is our source of light, we'll draw wave fronts coming off of that source of light. So these are the wave fronts. Specifically, what we're showing here when we draw a wavefront is that a wavefront indicates a set of points on a wave that are in phase with each other. So typically, this would be the peak of the wave. In other words, when I draw one of these wavefronts, what I'm saying is every single point along that wavefront is at the peak of the wave's oscillation. Now, along with that, we have rays. What a ray shows you is the direction of travel. Which is always going to be perpendicular to the wavefronts. So here would be a ray, perpendicular to those wavefronts, okay? So now that we have this basic way of visualizing a light wave, we can move on to the law of reflection. And this is a really simple statement that when light reflects off of a surface, the angle of incidence equals the angle of reflection. So angle of incidence equals the angle of reflection. Okay, it's that simple. So the picture to have in mind is you have a surface that is reflective. We draw a normal line to that surface like so. So here's the surface, here's the normal line. And then we have a light ray coming in and striking the surface. So we measure the angle of that ray, which we call the angle of incidence, theta I, relative to the normal line. And then after reflecting, the ray goes off like this. Okay, that's the reflected ray. The angle of that reflected ray relative to the normal line is theta r. So what we have is theta I equals theta r, where both are measured relative to the normal line. Okay, and that's how reflection works. Okay, now refraction, let's actually just explain what refraction is. So any wave can refract, and when we say there's refraction happening, we're saying there's a change in direction of a wave when traveling into a new material. In other words, a light ray will become bent when it travels into a new material. And the way we can understand how this works is that this is governed by Snell's law, which states that n1 sine theta 1 equals n2 sine theta 2. Those n values are what we call the indices of refraction. So the picture to have in mind is we have two materials. This material, let's call it N1. This material down here, we'll call it N2. And the boundary between them is what we call the interface between the materials. Just like before, we draw a normal line to that interface. And then we have an incoming ray, which makes some angle relative to that normal line. Let's call it theta 1, because it's on the same side of the interface as N1. And then to show that we have refraction happening, the ray gets bent. It's moving in a new direction after going into the new material, which is at an angle theta 2 now, relative to the normal line. That's refraction. And again, if we want to relate those two angles, we use Snell's law as shown here. So the next chapter that we covered was chapter 33 on optical instruments. So I'm talking about things like mirrors and lenses. So we'll start with thin lenses. So what is the sort of physical principle behind the way a thin lens works? Well, it's based on refraction. A lens is typically made out of glass, so light will refract when going from air into the glass. and we can take advantage of that to focus light. So there are two basic types of lenses. We have converging and diverging lenses. And the difference between these is in the sign of the focal length that we use, at least in terms of our equations. F is positive for a converging lens and negative for a diverging lens. So as an example, let's draw a converging lens, which would look something like this. It would have a convex shape. And we draw this line, which is called our optical axis, going through the center of the lens. And let's show the focal point of our lens with equal distance on the right and the left side. So the first thing we do is draw the object. For this example, let's say that the object is outside of the focal length of our lens. And the height of the object is what we'll call HO. Whereas the distance from the object to the lens is what we'll call DO. Now, if I want to understand how this lens forms an image of the object, I can draw a ray diagram. I can draw three principal rays. The first one goes like this, parallel to the optical axis, and then out through the focus. All right, the next one starts going through the focus on this side of the lens, but then after going through the lens, goes out parallel to the optical axis. And we can already see where the image is forming, but let's just draw the third principal ray, which goes straight through the center of the lens without any change in direction. So this is a ray diagram, and we can see where the image is forming. Now, we started with those rays coming off the tip of the arrow. So this is where the image of the tip of the arrow will be forming, meaning our image is inverted. So this is what we call a real and inverted image. It's real because we actually have rays converging at that point, but it's inverted because the arrow is flipped upside down compared to its original orientation. We also have DI, which is the distance between the lens and the image. And then one last distance that we should just take note of here is F, the distance between the focal point and the lens itself. So there's something called the thin lens equation that we can use to relate these three distances. The thin lens equation says that 1 over F equals 1 over DO plus 1 over DI. Another thing we might be interested in is the magnification of the lens. So in other words, we have HO for the height of the object. We also have HI for the height of the image. How do those two relate to each other? Well, the definition of lateral magnification is just that ratio. So we have lowercase m equaling HI divided by HO. It turns out that ratio of the image to the object height is also equal to the ratio of the image to the object distance, except there's a negative sign out there to make sure our conventions work out. So in addition to lenses, we also have mirrors. So in particular, we learned about spherical mirrors. In other words, where the reflective surface is a section of a sphere. These are based on reflection, of course. So if we want to understand the ways that the light rays travel after bouncing off of a mirror, we just need to understand the law of reflection. So just like before, we can have a converging or a diverging mirror. I'm going to show, just for illustrative purposes, a converging mirror once again. And then here's the optical axis. But what I'm going to do is put the object inside of the focal point of the mirror. So imagine this is the focal point. This is our object here. What kind of image gets formed by the mirror? Well, just like before, we can draw three principal rays. So the first one goes parallel to the optical axis like this, and then out through the focus like this. The next one starts going through the focus on this side, or at least it follows a line that would go through the focus like this, hits the mirror, and then goes out parallel to the axis like that. And then finally, we have a ray that hits the center of the mirror, and we just remember that the angle of incidence equals the angle of reflection, so the optical axis will now just serve as our normal line. And there we have it. So notice how the outgoing rays are not converging. Okay? But if we trace them back, we trace those outgoing rays back behind the lens, or behind the mirror, I should say, like this. Now we see that those virtual rays are converging. So that means we have a virtual image. So here's our object over here. We have an upright virtual image on this side. And that's just one example of the type of image that can be formed by a mirror. Now, what are the equations that govern mirrors? Well, the nice thing is we're governed by the same set of equations as with lenses. Meaning, I can use this equation to calculate where the image forms, what's DI, for example. And then I can use this equation to calculate the lateral magnification of a mirror. So the same set of equations apply. The last thing to say about this is that if we have multiple lenses or mirrors, so if you're constructing something like a telescope or a microscope, for example, how do we deal with that? Well, it's pretty simple. The image that's formed by one instrument, so the image formed by one instrument becomes the object for the next. So basically, you treat each one at a time using this sort of analysis that I just outlined, and that's how you can deal with a system with multiple lenses or mirrors. So then we move on to chapter 34, which is all about interference of light waves. So it all starts with the principle of superposition. This is the idea that when two or more waves meet at the same location in space, we can simply add their displacements. Now, one way this can happen, let's say we have two waves. So the first wave looks something like this. And the second wave is completely identical to the first wave. And their peaks line up with one another. So anywhere you see a peak on the first wave, there will also be a peak on the second wave. So this is what we call constructive interference.
because the result of adding these two waves together is to get a wave with a bigger amplitude than what we started with. That's why we call it constructive interference. So the condition that has to be met for constructive interference to happen is that the phase difference between the waves, which we call delta phi, is equal to 2m pi, where m is 0, 1, 2, and so on. So let's take a closer look at that. If we plug in m equals 0, that means the phase difference between the two waves is exactly 0. If we plug in m equals 1, we get 2 pi. So if the phase difference is 2 pi, the peaks still line up in the exact same way we showed before, because if you add a phase of 2 pi, you don't really change anything. Same with m equals 2. You get 2 times 2 times pi, or 4 pi, which again would still give you constructive interference. So this is the most general way of stating the condition for constructive interference. Now, on the other hand, if we draw the first wave like so, but the second wave is identical but shifted compared to the first, where the peak of one wave lines up with the trough of another. So now when you add the two waves together, you're adding a positive displacement to a negative displacement, and the waves are effectively canceling each other out, which is what we call destructive interference. So rather than getting a wave that has a bigger amplitude, we actually get a wave with a smaller amplitude than either of the individual waves. So what has to be true in order to have destructive interference is that the phase difference between the two waves, delta phi, is 2m plus 1 times pi, for m equals 0, 1, 2, and so on. So if you plug in m equals 0, you get delta phi is equal to pi. So if the two waves are pi out of phase, that's when you get the peak of one meeting up with the trough of another, and they get canceled out. 3 pi also works when you plug in m equals 1, or 5 pi. Any odd multiple of pi, basically, is how you get destructive interference. So one application of this is in the double slit experiment, where we have a screen called the slit screen with a pair of narrow slits in it. And the slits are separated by a distance d. And then over here we have what's called the viewing screen. Now, if we draw a line from the very center of the slits to the viewing screen like this, we can measure an angle relative to that line, which we call theta. Okay? Now, the idea behind the double slit experiment is that you have two sources of light waves. Okay, you're going to have a wave coming out of slit number 1 up here, and you're going to have a second wave coming out of slit number 2 down here. Depending on the phase difference between the waves, you may have destructive interference or you may have constructive interference. You see a bright spot where you have constructive interference, so you'll have one of those bright spots at the very center, and then a dark gap, and then another one, another bright spot, and then another dark gap, and then another bright spot, and so on. You get this pattern of bright and dark spots, which we call the interference pattern. And one thing that we worked out in class is that the bright spots are located at angles where d sine theta equals m lambda for m equals 0, 1, 2, and so on. So basically, where did this come from? It came from applying the constructive interference condition, because we have bright spots, to this situation. And we ended up with this formula after going through a derivation. Now, the other type of interference that we covered is called thin film interference. So here's how that looks like. So we have a thin film of some sort of material. The thickness of that film is T. And then we have some light coming in and striking the thin film. So one thing that can happen is that the light can just immediately reflect off of that thin film. And let's call this reflected wave number 1. But another thing that can happen is the wave can go into the thin film, reflect off this lower boundary, then go back out into the air. And so that would be reflected wave number 2. So what we're dealing with is interference between reflected waves number 1 and 2. So the reflected waves 1 and 2 can either interfere constructively or destructively. So when you have constructive interference, you see a bright color. When you see destructive interference, you see a missing color. So you don't see any reflected light there. And either one of these things can happen, again, depending on the phase difference. So I'm not going to go through the details of this. I'll just make a note that you should know how to calculate or how to work out the formula for delta phi, the phase difference between those two waves in this case. So again, that's back in the chapter 34 notes. There are a lot of details as to how to do this. I'm not going to cover those here. It's just something you should know how to do. So next, we'll move on to chapter 35, which covers diffraction and polarization of light. So what is diffraction in the first place? Let's start there. So diffraction refers to any situation when a wave bends around an obstacle or spreads out after going through an opening. So if a wave bends around an obstacle or spreads out after going through an opening, that would be an example of diffraction. And this can happen with any type of wave, including sound waves or waves on the surface of water. But specifically, we're going to think about diffraction when it comes to light waves. So one of the main tools that we used to analyze diffraction was a Phasor diagram. Now, a Phasor diagram is a useful tool for seeing how waves add together. So the basic idea is that a wave is represented by an arrow. The amplitude of the wave corresponds to the length of the arrow. And the phase of the wave corresponds to the angle of the arrow. And what we use to add waves is the tip-to-tail method. So just as an example, let's say this arrow represents the first wave with amplitude A1. Let's say this arrow is the second wave with amplitude A2. And I show it pointing in a different direction to denote that the first wave and the second wave are not exactly in phase. There's an angle between them. And if we had a third wave, then that would just be another arrow in the diagram connected tip to tail with the last one. Let's say that one has amplitude A3. So the total amplitude, when I add all these waves together, is given by this arrow, which goes from the start of the first arrow to the end of the last arrow. Okay, so this is how we can deal with any number of waves being added together. You can have 2 waves or a billion waves being added together, and you can still use this basic technique. Which takes us then to single slit diffraction. So here, the situation is we have a screen with just a single narrow slit in it, and the width of the slit we call A. And then we have a viewing screen. So the idea would be that I send some light through the slit and project it onto the viewing screen. Now the surprising thing is that rather than just seeing a spot of light at the very center of the screen, we actually get a diffraction pattern. So at the very center of the screen, we have a bright spot, followed by a dark spot on either side of that, then another bright spot, then another dark spot, then another bright spot, and so on. That pattern just continues. This is called our diffraction pattern. That's a series of bright and dark spots, but it's not exactly the same as our interference pattern from before. Some of the details are different. So in particular, we have dark spots, points of destructive interference, located at angles where A sine theta equals m times lambda. So again, these are the dark spots. And m is equal to 1, 2, 3, and so on, but not 0. So 0 is not included in that formula. As before, we're talking about an angle theta measured off the center line like this. So that formula tells us where the dark spots will be located. Another thing we derived is the intensity at any point within our diffraction pattern. This is given by I equals I naught, so that's at the center of the pattern, where the angle is equal to 0, times the quantity sine beta over 2 divided by beta over 2, all squared, where beta is equal to 2 pi divided by lambda times A sine theta. So slightly complicated, but what we have here is an equation that you can just plug an angle into, and it will tell you what the intensity is at that particular angle. Now, remember how we got this? We derived this by adding an infinite number of phasors together. Because if you think about what's going on here, we have a slit, and each point along the slit can be considered to be a source of a wave. So if we really want to understand how these waves destructively or constructively interfere to give you either a dark spot or a bright spot on the screen, we really have to think about how to add an infinite number of waves together. And again, we did that using a Phasor diagram, and these are the results we got from that analysis. Okay? So that's single slit diffraction. Now, the next thing we're going to note is that light also diffracts through a circular aperture. So not just through a slit, but through circular openings as well. Now, if you think about it, all kinds of optical instruments involve light diffracting through a circular aperture. If light comes in through your camera, or through a telescope, or through the pupil of your eye, that light is going through some sort of circular opening. So that's where the Rayleigh Criterion comes in. The Rayleigh Criterion says that two sources are just barely resolvable if the angle between them is greater than theta min equals 1.22 times lambda divided by d, where d is the diameter of the aperture, and lambda, of course, is the wavelength of the light. So the picture you should have in your mind is that we have two sources. Maybe they're two stars we're looking at in the night sky. They have to be a certain distance apart, a certain angle apart, theta min, in order to actually be able to resolve them as two separate objects. Because the light from each one of those sources is going to be diffracting through the circular aperture. That's going to blur the light. It's going to make it spread out. And so if the angle is too small, those two diffraction patterns are going to be right on top of each other. There really won't be any way to distinguish them from each other. We're not going to be able to see these as two distinct points of light. But if the angle is at least this big, then we'll be able to distinguish them as two sources of light. The last thing to note is that when we calculate this angle, it comes out in radians. Okay, so the last topic that we covered in this lecture, chapter 35, is polarization. So the polarization of a wave refers to the direction of its oscillation. Okay, so let's say we have a transverse wave like this. The wave would be moving to the right, so that would be its propagation. But its oscillation would be happening in this direction. So the direction of the oscillation is what we call the polarization of the wave. So there are two situations that I want to remind you of. If we have unpolarized light, which just means we have a mix of different polarizations so that there's no preferred direction. Unpolarized light going through a filter looks something like this. So we show that the incident wave, the one that's coming in as unpolarized, by showing a set of crossed arrows like this. That represents unpolarized light. So this is our incident wave. The intensity is II. It goes through a filter. We show the axis of the filter with a set of lines like this. So the light that gets transmitted is completely parallel to the filter. What gets blocked is the light that's perpendicular to the filter. Anything that's polarized perpendicular to the filter gets blocked out, so we're only left with this transmitted wave, which is now polarized along the filter. And the intensity of that transmitted wave, which we'll call IT, let me write that again, IT, intensity of the transmitted wave, that would just be 1/2 of the incident intensity, okay? So that's what happens when you have unpolarized light going through a filter. Now, if we have polarized light going through a filter, this is what it will look like. So first of all, the incident wave is going to be shown with just a single arrow like this to indicate that there's just one direction of polarization. That's the incident intensity, II. Here's the filter. And so what we'll note is there's some angle between the axis of the filter and the polarization of our incident wave. Call that angle theta. And then a wave gets transmitted through the filter. And again, it's polarized along the axis of the filter. And the intensity is IT. But in this case, the transmitted intensity is the incident intensity times cosine squared of the angle theta. So when it comes to polarization, you should know how to deal with unpolarized light going through a filter and polarized light going through a filter, and how to use these for different combinations of filters. And that takes us to the very last chapter of the semester, chapter 36, which deals with the theory of relativity. Now, Einstein's theory of relativity can be very counterintuitive and sometimes difficult to wrap your head around. And so for that reason, let's go to the very basics. What did Einstein base his theory on in the first place? Well, the foundation that the theory is based on is actually pretty simple. The theory is based on the fact that the speed of light in a vacuum which we call c, is really a constant, meaning it's independent of the speed of the source of that light or the observer. Okay, so no matter how you're moving relative to the source of the light, you're always going to see the same exact speed for that light, which is kind of strange if you think about it. So if we sketch out a scenario where someone is standing on a train like this, and the train is moving forward, let's say at half the speed of light, and let's say the person riding on the train has a flashlight, and they shine it forward in that same direction. What would someone who's just standing there on the train tracks, what would they see? Well, according to Newtonian physics, we should basically add the speed of light relative to the train, which is c, to the speed of the train relative to the ground, which is 0.5 c, and we'd conclude that the person standing on the train tracks sees the light beam coming towards them at 1.5 c. But that actually is completely wrong. Okay, this person on the ground still sees the light beam approaching at a speed c. Now, as strange as that idea might seem, it's actually been confirmed by many experiments. The most famous one was the Michelson-Morley Experiment, which again showed that regardless of how fast the source of some light is moving relative to you, you will always measure the same exact speed c for that light beam. So what Einstein did was he accepted that the speed of light truly is a constant. Every observer is going to agree on that speed c. But as a consequence of that, our ideas about space and time are going to have to change. So the first relativistic effect that we learned about is called time dilation. So this is the idea that two different observers are not necessarily going to agree on the amount of time that has passed between two events. So the way we write this is delta t is equal to gamma times delta t naught. So delta t and delta t naught refer to some sort of time interval. And gamma is a constant that appears all the time in the equations of relativity. It's equal to 1 over the square root of 1 minus v squared over c squared. So that's the gamma factor. Now, delta T naught is what we call the proper time. And it's the time between two events measured in a frame, so a frame of reference, where the two events occur at the same location. Okay, so delta T naught is the proper time. Delta T would be the time measured in a different frame of reference, which is moving at speed v relative to the first frame of reference. That's the idea behind time dilation. The amount of time that elapses between two events, delta T, is going to be different depending on which frame of reference you're in. That's the effect of time dilation. We also learned about length contraction, which is the idea that two different observers in two frames of reference won't even necessarily agree on the length of an object or the distance between things. So the way we sort of express this is L equals L naught divided by gamma. So gamma is the same as before. And L naught is what we call the proper length. So this would be the length of an object measured in a frame of reference where the object is at rest. That's L naught. So L would be the length measured in a frame where you see the object moving, and what you'll see is a shorter or a contracted length. The last thing to note about this is length contraction only happens along the direction of motion. So any length perpendicular to the direction of motion is not going to be changed. Okay. The next thing we learned about was relativistic velocity addition. And the very first example I gave you up here with the person on a train shining a light towards another person kind of illustrates the fact that the way we add velocities in Newtonian physics breaks down when things start to move close to the speed of light. So the correct way to add velocities is given by the following equation. We have VOA equals VOB plus VBA divided by 1 plus VOB times VBA divided by C squared. Okay, so first of all, what's the notation here? We have two subscripts. So for example, if I'm talking about VOA, that would be the velocity of an object, which we label as O, measured in a frame of reference, which we call A. So VOA means the velocity of the object relative to frame A. And that's how the notation works with the two subscripts. Now, one consequence of this new way of adding velocities is that velocities greater than c, faster than light travel, in other words, are just not possible. Okay, this equation, as well as the other equations of relativity, just don't allow for faster than light travel. The last thing to say about this is this equation is a one-dimensional equation. So it only works if the motion is along a single line or in one dimension. Okay. Now, in addition to having to sort of rethink our ideas of space, time, and how we add velocities, we also need to rethink our whole notion of dynamics, things like energy and momentum. So let's talk a bit about relativistic dynamics now. So the first thing that we went over is momentum. So in order for conservation of momentum to still make sense when things are moving close to the speed of light, we actually have to revise the definition where P is now gamma times mv. Now, of course, if the speed of our object is a lot less than c, okay, we're not even close to the speed of light, this reduces to the classical formula, which is P equals mv. And in fact, that's going to be true of everything we see in relativity. In the non-relativistic limit, that's what we call this right here, where the speed is much less than the speed of light. Everything that we see in our relativistic formulas reduces back down to the classical formulas from Newtonian physics. So another example of that would be kinetic energy, which is in relativity given by K equals gamma minus 1 times mc squared. Again, when V is much less than C, then this formula reduces to the classical formula 1/2 mv squared. Okay. The next thing we need to realize about the way energy works in relativity is that the total energy of a moving object actually consists of two parts. We have the kinetic energy, the energy associated with motion, but also something called the rest energy, which is sort of new in relativity. So what are some of the formulas here? Well, the total energy, as we derived, is given by E, and this is equal to gamma times mc squared. Whereas the rest energy, which is what we call E naught, is just given by mc squared. And that's Einstein's famous equation. This basically says that there is an equivalence between mass and energy. In other words, the amount of mass an object has is simply a function of its rest energy E naught. And if that rest energy changes, then the mass also changes. So our whole idea of mass in relativity has to be rethought. Mass is not just how much stuff something is made out of, but it's also the energy content of that object as well. And then the last thing we derived is the famous energy-momentum relationship. Which relates all of these different ideas. It says that E squared, that's the total energy squared, equals P times C squared plus mc squared quantity squared. So how do we think about this? Well, the equation looks remarkably similar to the Pythagorean theorem. So in other words, we have a right triangle where the hypotenuse is the total energy, and then the two other sides are mc squared, which is the rest energy, and then P times C, which is just the momentum times the speed of light. And this is what we call the relativistic triangle. So we can visualize how to relate these different quantities.
And so that does it for Physics 47. Now, I know that for a lot of you, this will be the last physics class that you ever take. So I want to leave you with some final thoughts. Now, back in 1905, when Einstein first published his theory of special relativity, it completely revolutionized the field of physics because it forced people to challenge some of their most basic assumptions about the way space and time work. Now, around the same time, in the early 1900s, there was another revolution going on called quantum mechanics. And so quantum mechanics, in a lot of ways, is an even more strange and counterintuitive theory than relativity, but it's also really interesting because, again, it challenges some of our basic assumptions about reality at the basic level. And it took until about the late 1920s for quantum mechanics to become a fully mature theory with all of the equations worked out. But ever since then, we've been living in what's called the modern era of physics, where everything is fundamentally based on the framework of relativity, which includes the theory of special relativity as well as general relativity, and quantum mechanics. And so part of the challenge of the modern era of physics has been to see how these two theories fit together. How can we get relativity and quantum mechanics to work together in a more comprehensive theory? And there's been a lot of progress on that front over the last 100 years or so, but there's still a lot of work to be done. In particular, we don't know how quantum mechanics fits in with general relativity, which again is a theory of gravity. And because we don't really know how general relativity and quantum mechanics are supposed to fit together, there's still many unanswered questions in theoretical physics. So, for example, we don't really know what's going on inside of a black hole, in particular at the very central point called the singularity. In order to understand what's going on there, we would really need to just go beyond our current theories. And that is to say that there is still a lot of important work to be done in theoretical physics. And I'm sure that throughout your lifetime, there will be many interesting developments happening. Some of them you might read about in the news. So I hope that even if you don't continue taking physics, you will continue to read about some of these things, maybe even pick up a book on quantum mechanics or watch a documentary on it if you're interested. And I hope that the physics sequence at Chaffey College has helped prepare you for whatever's coming next, whether that be an engineering degree or anything else you might be pursuing in the future. I also hope that after taking the sequence, you have an appreciation for the physics of everyday life, how all this stuff that we've learned about over the last few years can be applied to everyday situations to help understand how the world works. Also, I hope you've gained some appreciation for some of the more abstract and theoretical side of things, which doesn't necessarily have, a practical application, but can be really interesting nonetheless. So with that said, we'll end the video here. I'm going to wish you all good luck on your finals, and I hope, as always, you're being safe, being healthy out there. Take care.